In this tutorial, we learn how to turn spacecraft images of solar system objects into realistic simulations of Earth-based observations with ScopeSim. In the first part, we'll use an image of Jupiter's moon Io taken by the Galileo mission and simulate how it would appear if observed with MICADO on the ELT. This is a simple use case on how to prepare a fits image for ScopeSim, construct the correct angular scale, and simulate a realistic MICADO observation. To get started, we import our usual packages, NumPy, Matplotlib, and AstroPy. Optionally, we also define two small helper functions. The first one simply converts astronomical units into kilometers. We'll need this because the spacecraft image has to be rescaled to the apparent size the object would have when viewed from Earth. The second helper function is a custom plotting routine. We'll use ScopeSim's built-in plotting function for quick visual checks, while this additional function lets us display the final image in angular coordinates and directly see the apparent size of the source on the sky. Next, we load the fits file containing the Galileo image of Io and take a first look at it. As usual, you'll find the sources I used linked in the video description. Looking at the file structure, we can see that the image is stored in the primary HDU, so we will work with this. I usually define the header and data immediately, but feel free to skip this step. We also need to convert the data to floating point values before processing it further. Finally, we normalize the image by dividing each pixel by the total flux. The header doesn't contain a lot of information, but the observation includes a label file containing additional metadata. From this file, we obtain two quantities: the spacecraft distance to Io, which was about 555,000 kilometers, and the image scale of roughly 11 kilometers per pixel. Dividing this image scale by spacecraft distance yields an angular pixel scale of 4.17 arcseconds per pixel, which we can now use to display the image with the correct angular scale. This is Io as seen by Galileo from a distance of roughly 500,000 kilometers. Our goal, however, is to simulate how Io would appear when observed from Earth with MICADO. Each image pixel corresponds to approximately 11 kilometers on Io. That image scale remains unchanged. From Earth's much greater distance, however, it corresponds to a much smaller angle on the sky. Assuming an Earth-Io distance of approximately 5 astronomical units, we calculate this angular pixel scale and store it as the CDELT value in the fits header. We now update the fits header with the minimum world coordinate system information required by ScopeSim. We specify that the coordinate units are arcseconds, insert the CDELT value we just calculated, place the reference pixel at the center of the image, set the reference coordinates, and define the linear coordinate axis. With that, the image contains all the geometric information ScopeSim needs. Now we're ready to move to ScopeSim. We create an image HDU using the modified header together with the image data. This image becomes our source, and we assign Io its apparent brightness of approximately magnitude 5. Next, we initialize the MICADO simulation. We'll use two exposures of 30 seconds each. Since Io only occupies roughly 300 detector pixels per side, we reduce the detector window size. Then we simulate the observation and do a quick visual check. We can see that the source is bright enough to saturate the detector, and as the original image already suggests, it is not centered. So let's go back to the point where we created the source and use ScopeSim's shift command to apply a small positional offset. A shift of 0.6 arcseconds in both x and y direction is sufficient. We also enable MICADO's neutral density filter in the pupil wheel to prevent the detector from saturating. If we do another quick check, this looks much better. Now to get this picture in gray with the corresponding angular scale, we use the plotting function. And this is our final simulated MICADO observation of Io. The same workflow can be applied to virtually any solar system object. As long as the image scale and observing geometry are known, spacecraft images can be transformed into Earth-based telescope observations. In part 2 of this tutorial, we will look at how to overcome obstacles in a less straightforward example on Titan.